Today we want to continue in section 1 with the last section of that particular chapter, which would be section 1.10, modeling with functions. And constructing functions from verbal descriptions here. Taking a look at word problems. We have a word problem here, and we want to be able to identify just the language here. And it says you are choosing between two long distance telephone plans. Plan A has a monthly fee of $20 and charges 5 cents per minute. Plan B has a monthly fee of $5 and charges 10 cents per minute. And what we want to determine is which is the best plan, or at how many minutes are the plans equal. So here we actually can have the fixed cost plus the variable cost here is equal to the fixed cost plus the variable cost of B and A, and we solve for X, and we get that X is equal to 300 minutes. So at 300 minutes the plans are actually equal. And we can actually graph this by, I'm going to bring up the TI, and we can graph this function here. If we look at y equal, I'll drop it down a little bit, and we set one function equal to y1, which would be 0.05x plus 20, and the second function is going to equal 0.1 plus 0.1x plus 5, and we'll just do a zoom fit, and we can see, we actually can't see the values in the window here, so I'm going to change the window settings to reflect the values here. I'm just going to go with the settings that's on the slide: 0, 500, 100, and then on the Y, 0 and 50, and looks like 5, and then we'll graph that function so we can actually see the intersection here. And if I do a second calculate, option 5, and just hit enter for the first curve, enter for the second curve, and enter, it actually gives me a value there of 300 for X value. So you can see that we can actually use the calculator to help us determine that value as well. Let's look at this equation here. We want to write the functions for men and women to solve the problem, and we look at the percentage of women in the labor force and the percentage of men. So here we have men and women, and we know that the decrease in yearly of men decreases by 0.25%, women increases by 0.5%. If there are presently 70 million men and 60 million women, then when will the number be equal? So we know that with the men, we have 70 million minus, and they're going to decrease by 25%, so we need to convert this to 0.0025, and X, depending on the number, is equal to the women, and the women are going to increase by 50%, so we're going to make that 0.005 times 60 X, and we solve in terms of X, and we're going to end up with, looks like approximately 400 over 19, or approximately 21 years. So in 21 years from, looks like from year 2000 is where it was selected, because that's when the women had about 60, the men had approximately 70. So in 21 years from year 2000 is when the population will be equal. This particular slide here shows the TI 84, and we make one equation y1, one equation y2, and we do a second calculate and intersect, and we get the same answer there. A local telephone company charges 11 cents or $11 for local phone calls and 10 cents each long distance call thereafter. A second company charges $14 and then 5 cents, and so we want to find out how many minutes of long distance would they be equal. So we can look at the local company. It's 11 plus 10 cents times each additional minute is equal to 14 plus 5 cents for each additional minute, and we solve for X, and we'll get 60. So at 60 minutes the plans are equal. Let's look at this example here. On a certain route, airplane carriers carry 6,000 passengers per month, each paying $200. A market survey indicates that if you increase each $1 in ticket price, the airline will lose 100 passengers. So one, we want to express the number of passengers in N as a function of X, and then the second one, express the monthly revenue R as a function of the ticket price. So what we have here is the ticket price is X, and we know that it's going to increase by $1 just depending on how many the ticket price itself. So X minus 200, and then the passengers here would decrease by 100. So we have 100 times X minus 200 there. We can actually rewrite the number of passengers. They're going to decrease. So we have 6,000 minus the number that it would actually decrease per 100, and that gives us the number of passengers in terms of X. And then we have the revenue per month, and we can take a look at that, the number of passengers that it's going to decrease, and we multiply that times X. If we graph this equation and we look at the maximum, we'll find out that the ticket price exceeds $130 for the maximum revenue. So this is our maximum point here, and we can actually calculate that point using the TI by doing the second calculate and entering in maximum. Any function in the form of a quadratic function in this chapter will yield a U-shaped graph. If it's a negative, it's going to yield a upside down U. If it's a positive, it's going to yield a U shape in the upward direction. Let's take a look at functions of formulas. Here we have a machine produces an open box of square sheets, and it measures 12 inches on each side. We're going to cut an equal size amount from each corner and then shape the box. So what we have is the volume is equal to the length times the width times the height. Of course, we know that formula there, volume of a box. So we have 12 minus 2x on the length, 12 minus 2x on the width, and then we have x on the height. And we can actually graph that there, and what that means is that the maximum size that this box can actually be is 128 cubic inches. So if we graph this particular equation, we can find the maximum point on the actual graph here. Let me bring up the TI to show you how to do that calculation. So y equals, I'm going to clear these two graphs out, and I'll just plug it in just as is, 12 minus 2x times 12 minus 2x. If you want to simplify this, you can, times x, and we'll do a zoom standard. Of course, you're not going to be able to see the graph in there, so let's do a zoom fit and see what we get. Okay, and we're actually wanting to take a look at the graph. See if they give us some window settings here, and we'll look at the window settings. X min, we'll make it 0. X max, let's make it 200, and then Y min, we'll make it 0, and Y max, we'll leave it 640. And let's graph it, and we can see, let me check my equation, make sure it's right. Sometimes we can't get the same equation here. Alright, that looks good. Let me check my window settings again. Let me see what they're using. They're using 0, 6, and 1, and they're using 0, 130. And we'll talk a little bit later on about how to generate these settings here so that you can actually get the graph just as is here. So now once we get that, we do a second calculate, option 4, which we want to find the maximum point. We move the cursor to the left of that peak, which we call that the left bound. Enter. We move the cursor to the right of that peak, which we call that the right bound. And then we hit enter to guess, and it actually guesses here. Notice that this value is fairly close to 2. The closer we get to that peak, the closer this value will be to 2, and then y is 128. So you can see that we have a similar graph here. And here's an example here, and we have the same example, and we want to let the volume equals, it's going to be 14 minus 2x times 9 minus 2x times x. So the volume in terms of x will be 4x cubed minus 46x squared plus 126x. So all we're doing is calculating the volume in terms of the length here. Here's an example where we take a rectangular and we want to model the area given a specific parameter. So here we have a parameter is equal to 140. So we actually plug it into the parameter formula because this thing can go several different ways here. So we know that the parameter is going to be 2 times the length plus 2 times the width. So we just let x equals the length, w equals the y equals the width. So we have 2x plus 2y is equal to 140. Solve for y. We take that and we plug that into the area, and the area formula here will be is equal to the length times the width, or in this case x times y. So we have x times y, which would be 70 minus x. So we write that in terms of x. So that's the area. We have a 300-foot fence, and we want to write the area in terms of x. So here we have 2x plus 2y is equal to 300. That's the parameter. We solve for y. Y is going to be 150 minus x. And then the area is going to be x times y. So it's going to be x times 150 minus x. So that's the area of the fence in terms of x. Now we also deal with simple interest in this particular section. Simple interest is equal to I is equal to the principal times the rate. So if we have, suppose we deposit $400, which we'll define that as P at 3%, that's R. We convert that to a decimal. That means that we'll gain $12 in interest here by multiplying 400 times 0.03. Now let's take a look at this example. A woman who's going to retire had $100,000 and she invested in a local bank, and she put money in a money market and at 3.5%. So this would be 3.5, and some in a certificate of deposit at 4%. So that will be 4% in the CD. And it says if the first year's interest is 3,850, how much did she put in each account? So we know we're going to have a total of 3,850. So now we can figure out the interest amount by multiplying. This is 100,000. So we multiply. We use the formula I is equal to PR, and we find the amount of interest, and we get 3,500. We take the difference here, and this will tell us how much interest is going to be in the certificate of deposit, which will be, looks like we'll put in 350, and let's see, then looks like she's gonna invest. We actually solve this in terms of P, figure out the principal amount. So we divide by R, so we get I over R, and if we do that, we get 8750 there. So 8750. So we're just basically filling in the blanks to determine how much money that she's going to actually have to invest there. We also deal with solids and surface areas in this particular section. We have a cube, a rectangular solid, circular cylinder, and then a sphere. And this is the surface area of each one of the expressions. And we know that the volume is equal to power squared times h. And if we have a can that has a 22 cubic inches, we substitute for V, solve in terms of h, and we plug this back into the surface area to find out what the area is in terms of R. And we can graph this function by writing it in terms of y, and then we can find out that the function is decreasing. We can get a minimum value here, and we can find out that it's actually increasing. So we have a cylinder can that can hold 50 cubic inches of oil, so that's going to be V, and V is equal to pi r squared H. So we solve this in terms of H, which means we divide pi r squared by both sides. So now we substitute back in 2 pi r squared plus 2 pi r, and then we substitute this in for H, 50 over pi r squared. And we solve that, simplified, we have 2 pi r squared plus 100 over r. So that's the area in terms of the radius, in terms of r. Now we can also calculate the distance using a parabola. We can calculate the distance from a specific point to a point, any point along the graph itself, as long as we know what the equation is, and we can specify a point there, and we can use the distance formula by substituting the equation into this particular distance formula here. We can also graph it as well. Once we substitute, and we can see what it looks like. Okay, let's take a look at this particular example here. We want to find the distance from the point on a parabola to the origin, express it as a function of x, and they give us the parabola, and it can be described as y is equal to x squared minus 3, where it intersects the y-axis at minus 3. So we have a point xy, and if we actually create a triangle here, then the distance is going to be the hypotenuse. So we know from Pythagorean theorem that the distance is equal to the square root, in this case, of x squared plus y squared. And now we just substitute the equation in place of y squared. So we end up with x squared minus 3 squared. And we can simplify that. And this would be plus x to the 4th minus 6x squared plus 9. And then we can rearrange it and combine our like terms, and we end up with the square root of x to the 4th minus 5x squared plus 9. So that's the distance from the origin to the point xy. Okay, let's take a look at this example here. If you invest a total of $2,000 in two accounts, one account pays $5,000, another account pays 5%, another account pays 3%. Write an equation that expresses the amount of interest that you will make in 1 year in terms of X, the amount invested at 3%. So we know that the interest on the equation, or on the account here, is going to equal 3% in one account, so I'm going to convert that to a decimal. So 0.03 in one account plus 5% in another account. Now we know that both accounts will equal $2,000. So if we solve this for y, that's how we express it in terms of x. We just subtract x from both sides. And now back into our interest equation, we substitute in place of y. We put 2,000 minus x, and we find one that apparently they just left it in that form there, so it looks like it's going to be looks like B or C. Actually, C will be our answer choice here. So the last one here, you have 400 meters of fencing to fence in a garden. Write a formula for the area of the garden as a function of x and its width. So we know that the area is equal to the length times the width, so we just say x times y. So we also know that it has 400 meters, which will be the parameter. So the parameter will be 2x plus 2y is equal to 400. And if we solve this in place of y, because we need to express it in terms of x, we solve and simplify, we end up with 200 minus x. So we go back to our original area formula, and in place of y we substitute 200 minus x, and we'll see that our answer choice here will be D. So this concludes section 1.10. If you have any questions, please email me. Thank you.